Hey there! You know those little moments where you see something and you just know there's a cool physics rule hiding underneath? Well, today we're going to pull back the curtain on one of those. It's a puzzle that shows up everywhere, from a simple game of pool all the way to the wild world of subatomic particles.
So, picture this. You're playing pool. You line up your shot. The cue ball smacks right into a stationary ball, and bam, they scatter. But have you ever noticed how often they seem to fly apart at a perfect 90-degree angle? Is that just a coincidence? Some kind of lucky shot? Or is there something deeper going on? Well, that is the exact mystery we're going to solve today.
And to really get to the bottom of this, we're going to deconstruct a classic problem. This one's from a legendary physics textbook, Irodov's Problems in General Physics. We're looking at problem 1.177, and believe me, it frames our little mystery perfectly.
Okay, so here it is, our challenge, and it's laid out in two parts. First, we've got to prove why a perfect, or as physicists say, an ideally elastic collision, gives us that clean 90-degree split. And then, for part two, we have to show why that perfect rule gets broken in a more realistic, inelastic collision. All right, let's dive in.
Now, before we can crack this case, we need to get our tools ready. And I'm talking about the fundamental, unbreakable laws of physics. These are the rules that govern every single collision in the universe, no exceptions.
First up, our most important tool, the law of conservation of momentum. All this really says is that the total oomph of a system before a collision has to equal the total oomph after. But here's the crucial part, the thing you have to remember. Momentum is a vector. Direction is everything. We're not just adding numbers, we're adding arrows.
Our second tool is the law of conservation of kinetic energy. Now this one's a bit special. It comes with a big if. It only applies to perfectly elastic collisions, those ideal perfect world scenarios. In those cases, the total energy of motion is also the same before and after. And unlike momentum, kinetic energy is a scalar. It's just a number, no direction to worry about.
And this right here, this is the key to the whole puzzle. And it's a spot where a lot of us get tripped up. For momentum, you're adding vectors, right? You're doing geometry with arrows. For kinetic energy, you're just adding up plain old numbers. Understanding that difference is going to make everything else click into place.
All right, our toolkit is ready. Let's start cracking this case. We're going to tackle part A first, the perfectly elastic collision. So just imagine two molecules colliding with zero energy loss to sound or heat or anything else. Just a pure, clean transfer of motion.
Now don't worry, I'm not going to flood the screen with a bunch of crazy equations, but here's the basic game plan. We write down our two conservation laws. Then we use a really slick algebra trick. We square the entire momentum equation. After that, we combine it with our energy equation and, well, something pretty cool happens. After all the math shakes out, we're left with this beautifully simple result. The dot product of the final two momenta equals 0. Now, if you're not familiar with it, the dot product is just a special way of multiplying two vectors.
So let's just pause here for a second. What does this little piece of math actually mean, like in the real world? What is it telling us about the directions those two molecules fly off in?
It means they're perpendicular. That's literally the geometric definition. If the dot product of two vectors is 0, the angle between them has to be exactly 90 degrees. So you see, the laws of physics themselves force that right angle to happen. Case closed for the elastic collision.
So, we've solved the ideal perfect world case. But, the real world is, well, it's messy. Billiard balls make a clack sound, right? They warm up a little bit. Energy gets lost. So what happens in an inelastic collision? This is the plot twist.
And this is the absolute key. In any real-world collision, kinetic energy isn't perfectly conserved. A little bit of that energy of motion always gets turned into something else, like the sound you hear, or a tiny bit of heat from the impact. And that means one of our fundamental rules has to change. So remember our second law, the conservation of kinetic energy? Well, it's not an equation anymore. It becomes an inequality. The initial kinetic energy is now greater than the final kinetic energy. The system has less energy of motion after the collision than it had before.
So when we go back and redo our proof, but we swap that equal sign for an inequality, everything changes. That beautiful, clean cancellation that gave us a 0 before, it's gone. It doesn't happen. The mathematical rule that forced the 90-degree angle is officially broken.
And that, right there, is the answer to the second part of our problem. The moment a collision is inelastic, the moment even a tiny bit of kinetic energy is lost, that angle will no longer be precisely 90 degrees. It might be 88, maybe 91, but it won't be 90.
Okay, so we've solved the puzzle from the textbook. Awesome. But what's the big picture here? Why should you actually care about this? What's the real takeaway?
Let's just quickly recap what we found out. Rule 1, momentum is always conserved. That's a universal law. Rule 2, kinetic energy is only conserved in perfect elastic collisions. So what this means is that for two equal masses, that 90-degree angle isn't just a fun fact. It's a definitive signature. It's a dead giveaway. It's a bright flashing sign that tells you that collision was elastic.
And this is where it gets really, really cool. This isn't just for pool players. Particle physicists use this exact principle as a powerful diagnostic tool. I mean, when they smash particles together in giant accelerators, they can't see the collision, right? But what they can do is measure the angles the new particles fly out at. That 90-degree rule helps them figure out what kind of interaction just happened. So I'll leave you with this. Imagine you're that physicist. You see two identical particles collide and fly apart at an angle of 85 degrees. What do you know? Instantly. You know with absolute certainty that the collision was inelastic. Some energy was lost. Maybe it created a new particle. Who knows? And that is the true power of understanding this 90-degree mystery. Thanks for digging into this with me.